Yes, hello. I'm very honored to speak in this online conference. So I remember actually 2 months ago there was a hybrid online conference from Cirm. Some people in Cirm, some people online, and now it's, I think, an online-only conference. I would have enjoyed to be at Cirm several times this year, actually, but we have to wait, I guess, until at least next year. So I'm going to talk on new subset constructions and very closely related on constructions of sets without arithmetic progression. And the title of this conference contains the word Diophantine problems. Well, I'm not really talking on Diophantine problems here unless you allow linear equations coming up. My constructions will be completely deterministic. So there is no probabilistic constructions involved, and if I don't forget, I will make a comment why random constructions are probably not useful in this connection. Anyway, I think I switch off my video. I think it irritates myself and maybe yourself as well, but okay. So first, when I talk about subset constructions, I would like to tell you what is a cap, and we talk about caps in affine and projective space, so I will tell you what that is about. Then I look at previous constructions by other people and explain to you the new subset constructions. And in the last part of the talk, very closely related, we study similar questions. Instead of caps, we just study point sets in Z modulo m to the n that do not contain an arithmetic progression of a given length k. Okay, I have to press that button. Yeah, this slide takes a moment to load, I guess, because there are some photos. So what is a cap? So actually, I tried hard to find nice pictures. So, well, a cap, this word really comes from the Italian and Latin. So cupola in Italian architecture is really the, say, this dome more or less looked from inside. I've also seen definitions like a bathtub just from the other side, inverted. Well, a cap is, of course, a head, and well, also this mathematical cap. So what's mathematical about this is essentially this shape. So if you use vocabulary like convex, that you know from convex sets, or so, a cap is a set of points that does not contain any 3 collinear points, no 3 points on any line. And if you write this in a more algebraic way, so there are no 3 points, call them x, y, and z, such that there is no linear equation lambda 1x plus lambda 2y plus lambda 3 times z equals 0, where the sum of the coefficients lambda 1 plus lambda 2 plus lambda 3 equals 0. So the most special, an important special case here is actually the arithmetic 3 progressions. So here you would have the coefficients 1, minus 2, and 1. So x minus 2y plus z equals 0. And the coefficients 1, minus 2, 1 add to 0. So an arithmetic progression is a special case. But of course, there are no 3 points on a line. That would also allow weighted progressions where the middle point is not really in the middle, but yeah, more, say, asymmetrical. And that can all be expressed in this with the coefficients lambda 1, 2, 3, which I mentioned. Yeah, so if you think of, say, any sphere, any ball, also if it's not just a round ball, but say a rugby ball, if you just think about the surface and you wonder, are there any 3 points in progression? So take any line intersecting this ball, whether it's really a sphere or a rugby ball, you will realize if there are no 3 points on a line, and that of course has to do with the shape, which is yeah, a strictly convex surface. Yeah, so the space I'm going to work on is here Z modulo P, usually for a prime, Z modulo P Z to the n. And you can think of this as just an n-dimensional cube, and where you have, say, as a base, an interval of length p, but the important thing about the interval is that you really reduce modulo p. And I want to show you how lines in this space look like. So the first left box here you can think of as a two-dimensional plane. It's a two-dimensional affine plane. And now if you have three such layers, think this now as layers stacked over another, which is really a three-dimensional cube then. And so there are some obvious lines, which are lines just also in Euclidean geometry. Yeah, the row, the column, and the diagonal. And there are more complicated lines. So if I look at these 3 points in this layer, so if you, for example, start here, you go one to the right, one to the one up, you are here, and you do that again, one to the right, one up, you are here, but then you reduce modulo 3 and you are here. And so this is a line, modulo 3. And even more complicated if you take the 3 colored points. So this point, go down 1 layer, and go 2 steps to the right, and then go down again a row, you are here, and then you do the same again, go down 1 layer, go 2 to the right, and go down 1 row. So these 3 colored points are an arithmetic progression, mod 3, but also they lie on a line mod 3. So this is more difficult to see, obviously. I mean, if you work on this, you get used to this. So here's another example, actually, of oops, yeah. So let's look at this now, and let's look at these 3 layers, still the cube, but these 8 points structured in this way, and just try to find any line. And if you continue any pair of points, say these pair of points, the third one isn't there, or these 2, the third one isn't there, or one from the top layer, one from the middle layer, and then one from the bottom layer. So there are no 3 points in an arithmetic progression. And such a set is called a cap. So, just by the definition of a cap, there are no 3 points on any line. And well, if you try to find, in addition to these 8 points, a 9th point, you will not succeed in this way. You cannot add any 9th point. But if you start in a quite different way, so here another cube, another 3 to the 3 cube. If you start in this way, actually you'll find 9 points. And 9 is the largest number of points without giving any 3 points on any line, or which is modulo 3 exactly equivalent without any 3 points in an arithmetic progression. So now if you play this game and try to do that in the 4-dimensional world now, so you have kind of 3 layers of 3-dimensional cubes, so this is now 4-dimensional, and here is the example of the maximal set. So there are 20 points, and this is best possible. And actually this is, sorry, no, something happened, I did not, okay, I have to press or hit a wrong button somehow. So these 20 points in the 4-dimensional space, those of you that know the card game set, this number 20 comes up there, and the set is 4-dimensional. So the previous cases, dimension 3 and 4, looked quite symmetric still, and this is the largest example in dimension 5, and it doesn't look that symmetric. Of course, there are some hidden symmetries, but it's not that super symmetric. So if you think you know how to generalize it in a good way from dimension 4 to 5 to 6, well, then maybe you'll find a family of good constructions, but very likely this is not the best construction, because it seems for each dimension one might possibly need a new trick to have some symmetry or not asymmetry. So this is a complicated game. And here is really the numbers of points in dimension 5. It's this number 45. In dimension 6, it's 112. And the proof that 112 is best possible actually is not so old. Yeah? That was included actually heavy computation. And the 7-dimensional case is still open. So it might be that one has a good construction, which is the maximum, but one cannot prove that it's the maximum. Anyway, if you have any such finite dimensional result, you can actually use a so-called tensor product construction. So, for example, if you have 9 points in dimension 3 and you aim now of making many points in dimension 6, you just take kind of a Cartesian product. Any combinations of 9 with 9 points gives you 81 points in dimension 6. And so in this way, you can lift any finite dimensional result to a multiple of this dimension. You know, from dimension 3 to dimension 6, dimension 9, dimension 12, you would get a similar result. Very simple. No new optimization needed. And from this, you could get something like an average increase of the number of points. And so 9 points was larger than 8, and the cube root of 9 is 2.08, and this is therefore kind of the average growth. So improving this, these finite dimensional examples also improves this kind of this average growth. So if you ask what's the best possible cap in a very high dimension, that's what you do. You try to find very good constructions in some low dimension. And actually here you don't have to prove that 45 is best possible. You just find a set with 45 points. And so you improve this, and then you see there is some further improvement. So the record is since many years now 2.217 to the n, and this is based on a 480 dimensional cap. But certainly in dimension 480, we do not know if this is best possible or not. Almost certainly not, actually. Yeah? So the exact values are only known up to dimension 6. All right. So here's a very brief history on upper bounds. So for a long time, 3 to the n over n times a constant was the record by Mechoulam, and then with very technical tools, this was improved by Bateman and Katz. And it was a long-standing open problem and frequently asked by important people whether the result shouldn't be much better, whether there is a positive delta so that the upper bound is 3 minus delta, so really strictly less than 3 to the n. This was almost solved, namely Krutlev and Pach solved in the case modulo 4. They adapted the polynomial method to this situation, and that was a breakthrough. And very soon after, Ellenberg and Geisweit actually saw that you can also adapt it now modulo 3 or modulo primes, or more generally in finite fields. Yeah, so it's based on the polynomial method, and really the mod 4 case, which is different from the mod 3 case, of course, but it contained the key for the polynomial approach. So we do not, of course, know what's the kind of the true order of magnitude. So in dimension modulo 4, z modulo 4 to the n, Peter Pach and I believe it could be 3 to the n. And the reason is we have a lower bound of roughly this size. And we have a heuristic reason why possibly the upper bound is sharp. But for dimension 3, I have not even seen a concrete conjecture about a best possible constant here. Okay, so far to upper bounds. You will see a similar slide again later. Anyway, so now we work in affine and projective space. Yeah, so if you work in combinatorics and number theory, you know that sets without 3 points in arithmetic progression are very well known, and this can be done in the integers, it can be done modulo m, it can be done in this multidimensional setting, which I'm studying here. But caps are, in dimension 1, are completely boring. I mean, if you have on an interval no 3 points, then yeah, you're not talking about it. So the affine space, affine geometry dimension and here now modulo p over the finite field with p elements. Well, we just think of it as the cubes that you saw earlier, modulo 3. So z modulo p is now the side length of the cube to the n, and just you don't need multiplication, you just need the additive structure. The projective space is a bit more complicated from this point of view. You say if you think of these 4 points as the 2-dimensional square, and then you add a line at infinity, so you add another 3 points here, and in this way, projective geometry, of course, was invented so that there are no parallel lines. Every so if you take this line and if you take this line, it's not parallel because it meets at infinity. This picture is called the Fano plane, and it's highly symmetric. So you could actually kind of invert every point could be you can show is isomorphic to every other point. So if you look at the incidences of how many neighbors does it have and what are the neighbors of the neighbors, you realize really every point could be mapped to any other point and gives an isomorphic copy. And also you could invert, you could change the role of lines and points actually. This is a picture of the projective space now with order 3. So here you see actually this 3 times 3 affine square. And then you add here 3 plus 1, 4 points at infinity. And then, I mean, the picture gets a bit messy because you have actually many lines. Every line has 4 points. And every point is incident to 4 lines. So it's highly symmetric. And the picture doesn't look super symmetric. And actually, when I looked at this just for the preparation of this talk, I found made by Wolfram Alpha or Wolfram this much more symmetric picture. So this is it should be the same picture. It's 13 points, but here you see lines. The lines are colored with the same color. The lines contain 4 points, and it's highly symmetric. And this also helps now if you want to study projective space planes with side length 5, but I mean you see lots of points. You see 31 points and you see 31 lines, but of course you need kind of now 31 colors for the 31 lines, and that it gets a bit messy. Anyway, so you don't need to be an expert on projective geometry. I'm also not an expert on projective geometry. I really come from the combinatorial world. So what you can think of, well, if you have, if you go to this projective geometry in dimension n with over the finite field with p elements, you have p to the n points, which is as a subset this affine space, and then you add points at infinity, and it turns out it's just this number, and this number comes from this quotient here. You add so many points at infinity, but if you just count how many points are there, you realize these points at infinity is a small part, so it's not even twice as big as the affine space. So if we want to improve the number of points in such caps, what we do actually now is we improve it in the affine case, and the affine case can be trivially embedded into the projective space. And the projective space could have possibly some more points, but we do not really care about it because our results will not be so precise anyway. They are asymptotically better, but optimizing by a factor of say 10% or something like this wouldn't matter for what we do. Anyway, if you look into the history now, let's look at the 3-dimensional case. And here Q is an odd prime power, so that there exists a finite field. And it's known that the maximal size of a cap in dimension 3 is Q squared, contains Q squared plus 1 points. And the affine case is almost the same, it's just remove 1 point. And the construction is relatively easy. So what you do is, well, if you write now in the projective case, 3-dimensional case, you have a homogeneous coordinate 1, so it looks like 4-dimensional. And then you have S and T varying over the field, which gives you then already Q squared many combinations. And the last coordinate now is this quadratic form. So think of it, maybe it looks like a shape, like an ellipsoid or something like this. And so because of this quadratic nature, it turns out there are no 3 points on a line. And what is A? A is a parameter, and you just must make sure that this quadratic polynomial is irreducible over FQ. Yeah, so you have lots of choices for A to do that. So this gives you Q squared points, and in the projective case, you add 1 extra point at infinity, which is this one. Yeah, and I actually, to understand that, sorry for myself, I just constructed here a simple example. So you take this quadratic polynomial, which is irreducible, and then you work out, I did it with Mathematics in a moment, you work out these 25 points. Yeah, so the last coordinate is always 1, and then you have 5 points with coordinate 3 here, and this coordinate is running 0, 1, 2, 3, 4 in all the cases, and this is the one that really has to be computed from this quadratic formula. And they have this last point at infinity, and if you now reduce to the affine case, you just remove the extra coordinate, which is just for the projective case, yeah, the homogeneous coordinate 1, and you remove this extra point, and you have your 25, your q squared many points. Right, so actually here again a comment on upper bounds. Yeah, so I said earlier, Ellenberg and Geiswart did the mod 3 case, Krutlev and Pach did the mod 4 case, actually earlier, just they started this business. And so then it was really generalized and optimized. So the method gives, if you do that modulo P, gives a constant times P. And this constant is a more complicated expression. It looks like this. And you optimize over a free parameter t, but it's a one-dimensional optimization procedure, and it's a constant like, say, 0.9. And when p increases, this jp decreases. It tends to a limit 0.84. Right. Also, we will actually observe in this talk that no 3 points on a line, which is the definition of a cap, is equivalent to no 3 points in an arithmetic progression. This was frequently known, of course, in the mod 3 case. The mod 3 case is really special. And the mod 4 case, this is almost true with some caveat, namely, you must say the arithmetic progression does not contain 2 times the same point. Otherwise, it could be that the first and the third point is the same. So you really talk about 3 distinct points in the mod 4 case. And in the mod 5 case, actually, I haven't seen that explicitly in the literature, but if you want to prove it, it's easy. Just do that. If you have 3 points, modulo 5, and whatever you do, so you can look at it as an arithmetic progression. And that actually helped me later to get a surprising result, modulo 5. Okay, so what is known about lower bounds? I mentioned the result by Bose in dimension 3. Yeah, so you have q squared. And no, actually, this c now is the maximum number of points in in the finite field fq dimension 3. Yeah, this is the notation for the maximum number of points. So if you have in dimension 3 q squared points, and you can lift it up to a multiple of 3, if the dimension is, say, 6 or 9, you just multiply q squared with itself several times. And now if n is increasing, you get really q to the 2/3 times n points. Yeah, so 2/3 is an exponent which you will see more or less a few times. This was relatively early, and Bose worked actually still on kind of combinatorial designs with applications for example, agriculture or something like these were the early applications of this. And there has not been much progress on this. Namely, you see here a result by Edel and Bierbrauer in dimension 6. So you would get from lifting this, you would get q to the 4, and they managed to get q to the 4 plus q squared minus 1 for this affine cap. So lifting this one now gives you in high dimension n a slightly better result than this one. Yeah, depending on q, it's not so much better. You will see some numerical estimates of this the space later on. That's not so much better because also, well, you think you add something, but you also take the 6th root of this. So the improvement is relatively small. Okay, so when q is 3 and q is 4, some better results are known. But these are the only cases. Yeah? So modulo q equals 5, 7, 11, whatever, nothing better is known. So Edel and Bierbrauer's result is more or less the record, apart from the special cases q equals 3 and q equals 4. Actually, when I say q equals 4 here, I mean the finite field. But in Krut, Lev and Pach, and I self-studied Z modulo 4, and Z modulo 4 is not the finite field. So these are 2 distinct cases with 4 elements, of course. So in the paper with Peter Palpach, so we have here a lower bound of 3 to the n over square root of n. And also we have a lower bound of modulo 5 of 3 to the n over square root of n. And I just told you a moment earlier, modulo 3, 4, and 5, the condition, an arithmetic progression, no 3 points in an arithmetic progression and no 3 points in a cap are equivalent. So actually, we first studied this just for arithmetic progression, got this result, and only after I realized this is a cap, this also, there are never 3 points on any line. So then I looked up what's the best possible result on caps, modulo 5, and from this one, it turned out it's slightly weaker. So this is 2.92 in the base. And I got a record, and I was very surprised actually, because at that moment I was not thinking about caps. But then of course the business started, and then joined with my PhD student Gabriel Lipnik. So we have now a couple of new cases, modulo 11, 17, 23, 29, 41. We get always an integer here, whereas the Beer-Brauer-Edel construction typically gets an irrational number. And of course, you need to compare in these cases which one is better. And here are the cases I listed. This gives new records. Unfortunately, this list is finite, so we have doubts that the method will be able to continue to many more primes. And also, there is a special thing about the primes. These are all 5 modulo 6. Yeah, so modulo 7, for example, we can apply our method, but it gives a weaker result. So the method, I would say, is, well, the previous method was you get a good example in a low dimension like dimension 6, and then you lift it up to higher dimensions 12, 18, 24, and you do something about other dimensions. What we do is not this lifting procedure, which seems to be weak from our today's point of view. So we think about, well, modulo p, we want to find certain good subsets of the integers, so we call them digits. And if you have a good subset of digits, avoiding a progression already in this space, then we can often say this avoids also progressions in the n-dimensional world. Yeah, so selecting a good digit set actually became an important part. And once we have a good digit set, then actually our cap will have size roughly d to the n divided by something small, which you can hide in this minus little of 1. Right, so here is a summary of the results. So C of fp to the n is the number of a maximal number of points, and we take the nth root of this one, and then the limit if n is large to get kind of the density. What's the increasing factor for each dimension? And Bose's result, for example, mod 5 was 2.92, and the improvement by Beer-Brauer and Edel was 2.94, and we got now 3, relatively easy. I'll show you the construction in a moment. So it's an improvement. And then you look at, say, at 11, here's a small improvement from 4.95 to 5. A more impressive improvement actually is for 23. So here we were lucky. This number is just close to 8, and we were able to get 9 digits. So we have here modulo 23, an improvement which looks much better than the previous improvements. But anyway, in improving just the space in the literature, something like this is called an exponential improvement. So when people talked about the upper bound, they called this an exponential improvement of the upper bound. And so we now have an exponential improvement of the lower bound. Yes, and Bose had an exponent of 2/3. So if you just think about, think of this as p to the 2n thirds, and if you take the logarithm and divide about the n, so this would in Bose's case give you the exponent 2/3. The mod 3 case, which is not listed here, is quite a bit better, is 0.72, and all other results are typically just as Beer-Brauer and Edel's construction, typically just a bit better than 2/3. And here are the cases, well, here the cases, the colored red cases are which are new. So this is, yeah, it's a small. It looks like a small improvement, but of course, again, it's an exponential improvement. And this modulo 23 case, this is the only case where you're really above 0.7, so it's almost close to the case mod 3 now. Right, so modulo 23, so the trivial upper bound would be 23, and until, say, 5 years ago, 23 to the n over something small was the best is known. So this, for this limit of this nth root, 23 was the upper bound until 4 or 5 years ago. So, yeah, Ellenberg and Geisweit, using the method of Krutlev and Pach, improved it to 19.64, which is an improvement of 40.6% of the upper bound, and our improvement in this case here is 11.2 for this base. No? Right, so this slide looks a bit ugly. So what we actually do is, so we choose a digit set D. Yeah, so we choose a subset modulo P, and also technically we do something else. We choose a subset of this set of the digits, but this is not so important. Think of D dash could be D, and you wouldn't lose much. And so if you have a good digit set, we can actually this digit set has the property that it avoids progressions and weighted progressions in the one-dimensional coordinate. And then with this extra trick, if you say, okay, you have here your point with these n different coordinates, and you say a constant number of them, yeah, so this is the number n over d times you fix this coordinate to be of a particular value. So you just say take vectors, so modulo 5, you take vectors where you say I take the coordinates 0, 1, and 2. And for some of these digits, you say, well, for example, for the digit 1, you say your vector of n coordinates contains exactly n over 3 many times the digit 1. Now, for some digits, you say it contains a fixed number of digits, fixed meaning n over the number of digits involved. And then actually working out how many of these objects of these points are there. This is really just taking certain binomial coefficients and multiplying this, and it looks complicated, but Stirling formula gives you this as d to the n, which is exponential, divided by n to some exponent, which is polynomial. Yeah, so it's essentially d minus little of 1 to the n. Right, so of course arithmetic progressions are a special case of this no 3 points on a line, and I come back to this definition of no 3 points on a line. So I said earlier I used letters lambda, but you could call them ABC. So there are 3 coefficients ABC, and they should add to 0, like here 1 minus 2, 1. And then there are yeah, points x, y, z, and this n-dimensional cube. And so that should not be 0. Yeah, otherwise, if it's 0, there would be 3 points on a line. And of course, the digit set ABC, which is just 0, 0, 0, doesn't play any geometric role. So instead of using these 3 coefficients ABC, you see it's enough if you restrict one coefficient, say a, to be 1. You know, just multiply by the inverse modulo p, and that works. So this is a simplification. So to avoid too many cases, you just say this digit could be 1, and you still cover everything. But then for the second coefficient, which is this new b, then after the transformation, you realize you still have p minus 2 equations, and therefore no arithmetic progression is one case, but now running over all possible values of b gives you many equations to consider. So your cap set avoids many linear equations simultaneously. So therefore you should expect this is more involved. So what we do, the set p now looks at all the kind of weighted progressions, yeah, weighted with the coefficient b, and x, y, z are just digits. X, y, and z are from d, and here you have such a weighted progression, which is a non-trivial one. Yeah, if you have x equals y equals z, that would not be interesting. You have here non-trivial weighted progressions in this set of p. And yeah, you do not really have to look at this. It just says that by symmetry, you can reduce it further. Namely, for example, if you have 2 points x, y, and z as an arithmetic progression, as a weighted arithmetic progression, you can actually look at another one, x, z, and y, which is also a weighted arithmetic progression with a different b. So this helps you reducing this case. If you are able to deal with the case B, you are then also able to deal with this related case. And there are some similar symmetries. This helps you reducing the number of cases. You will see an example in a moment. So let's do the case P equals 5 now, actually with the proof. We get three digits, 3 to the n over square root of n. And the example I choose is completely deterministic. I choose vectors with, or points with n coordinates, which I think are vectors with digits 0, 1, and 2. Yeah, digit 3 and 4 does not play any role. You can forget about this, but you reduce modulo 5. And the digit 1 occurs exactly n times, yeah, and you're in the dimension 3 times n. Yeah, so digit 1 occurs exactly the number of dimension divided by 3. Now, you have here the list of all weighted progressions you have to consider. And I told you earlier, some of these might be equivalent. And if you look at it, they are all equivalent. Yeah? So you really only have to care about one of these equations, namely, say, the progression case. Now, you list all arithmetic progressions modulo 5 using only the digits 0, 1, and 2. You have the trivial ones, and you have the more interesting ones. And then you look at the pattern more closely and you observe the digit 1 only occurs in the center position. Now, if you have a progression of 3 points and you must have somewhere of 3 distinct points, you must have somewhere a coordinate where there is some movement. Yeah? If you have an all coordinate constant 0, 0, 0 or 1, 1, 1, you would have the same 3 points. So in some coordinate, there must be a movement 0, 1, 2. Now, the first, the second, and the third point have the same number of ones, but the center point is lucky. It can easily get rid of a 1, but the boundaries, say the first and the third one, cannot get rid of the 1 unless we are in this trivial case of 1, 1, 1. So this shows all digits 1 occur only in this trivial progressions 1, 1, 1. So there is no moving progression like this. And therefore, if you have a progression, you have the trivial progression, namely 3 times the same point. So this is a complete proof that this digit set which I described is a cap. Here's the mod 11 case. So well, you have lots of choices for possible digit sets. Just avoiding progressions, you could choose 6 digits, but that's too optimistic. With this, you will not be able to have all the other progressions, so we actually use only 5 digits, but there are still lots of choices, of course. And actually, a subset of these digits, 0, 1, and 3, plays an extra role. Like in the last case, modulo 5, 1 played an extra role. We restricted the occurrence of 1 only, and here we restrict the occurrence of 0, 1, 3 only. So because of the 5 digits, we get 5 to the n, divided by n to the 1.5 because this special digit set has 3 elements. You write down all these weighted progressions with these 2, 3, 4, whatever coefficients here, and you realize some of them are equivalent. And actually, you have to care only about 2 cases. Yeah? So only 2 representatives of non-equivalent cases. One is the progression case, and you write down all the progressions modulo 11 now, with which lie in this digit set. And then you look at this carefully, and you see here, for example, the digit 1 occurs in the first and in the last position, but never in the center position. And then you play the same game I said earlier. So if the center case wants to get rid of a 1, then it must be in a trivial progression which is 1, 1, 1. So all 1s occur only in a trivial way as 1, 1, 1. So the 1 has to be removed completely. It cannot, a progression like this cannot exist. And then you go on, and then after removing this, you have this case and this case left. And then you see for the digit 3, you can play the same game. The digit 3 never occurs in the center. So these cases can also not exist. And then you have proof there is no non-trivial solution of this arithmetic progression. And you do a similar trick now for this weighted progression. It's colored, say all the 1s are in position in the first or in the second position, but never in the third. So there cannot be a weighted progression using a 1. And similarly, there cannot be a weighted progression using a 0. And then all of these weighted progressions are forbidden, and you are only left with a trivial case. Right. Yeah, so modulo 23 and modulo number 11, actually you can do by hand, but the higher cases are really more complicated. Here's some matrix which we studied modulo 23, but actually we did a lot of computer work there, and so some linear programming is involved. And otherwise we would not have been able to do any new digit sets modulo 23, for example. Right. Yes, so everything is completely deterministic here, extremely combinatorics in the sense I write down the example and you know immediately if the point is part of the set or not. What about probabilistic method? Could there be a random construction? I believe this is not the case. And the main reason for this is that also in the, a probabilistic construction would be good if there are many good examples, and using random methods to show them there exist many examples, so there exist at least one. But in this type of combinatorial problems of sets, avoiding certain patterns like progressions or caps, lots of linear equations, you do not have many good examples. You have a rather small number of good examples. And so you're searching like the needle of the haystack, in the haystack. And so this method is very likely not usable. So may I ask the chairman, Peter, how much time do I have? Should I stop here?
So you still have 8 minutes.
8 minutes. Okay. Ah, right. Okay. Yeah. Okay. Then I go on. Okay, if we do something in the modulo 4 case now, we also move away from the cap sets to the modulo to arithmetic progressions modulo 4. So here's the best example in dimension 3. It's a 3-dimensional cube, and there are 16 points. And actually, Sanders started this question more or less, Tom Sanders. So he knew Michelam's result, of course, which would give you the size of the cube, g, 4 to the n, divided by n, more or less, and he had an improvement on this. And the upper bounds usually use Fourier analysis. So he proved in particular little o of 4 to the n over n. And then people got interested in this. Sanders made a comment on lower bounds actually, and this would be as before. You take say this 3-dimensional example, you lift it, and with Pach we have been able to construct it in a way related to this case which I mentioned earlier, modulo 5. You take just the digits 0, 1, and 2. You have 3 digits, and you restrict the occurrence of the number 1. And in this way, you get 3 to the n over square root of n in this case, which is much better than lifting a low-dimensional example. And here we believe that really 3 to the n is more or less the upper bound. So we believe that if you take the logarithm of this and take certain limits, that 3 is the best possible base. Right, so on the case with no k progression, in this case z modulo m, but often m is a prime, and no k progression, the only result really we found in the literature is by Lin and Julia Wolf. And it is of this type. So if you look at this, you have seen that before in the sense of Bierbrauer and Edel. They were q squared, q to the 4 plus q squared minus 1. So this is the result they really use. They inject their result for caps. And then they realize that the caps, of course, do not contain a k progression. And so they get an asymptotic formula. If you simplify that a bit, you have more or less a base m to the k minus 1 over k and the whole thing to the n. So when I looked at this with Peter Palpach, we got for m is odd and m is even related results, slightly technically different. So here we have roughly m over 2 to the n. So m over 2 is a positive proportion of m, of course, whereas here the base would be m to the k minus 1 to the k, to m to the 2/3 if k is 3. So this case here is for 3 progressions. We can work out all the coefficients, but that's certainly not so important. And yeah, that actually, the modulo 5 case I mentioned earlier gave a cap, and that was surprisingly because at that time we didn't think about caps. And the even case, you have m plus 2 instead of m plus 1. So if m is very small, this is a decent improvement. And so for k progressions, I worked out first some individual cases, and I got 7 to the n over n cubed, and 7 was an improvement on this result by Lin and Wolf, which had 6.04. And then, yeah, now with my PhD students, Benjamin Klan and Gabriel Lipnik, using also computations similar to the one we had used for caps, we find good digit sets, and these digit sets you see are really quite a big improvement over the previous cases using a finite dimensional example in dimension 6, actually, this cap set construction by Edel and Lifting. And then we got interested, can we make this case of no k progressions general? So we now we want to avoid k progressions. We distinguish again 2 cases. K is odd, which is the better case, and k is even. So we can choose a digit set of this type. It's an interval. And again, of course, it's a relatively high positive proportion of m. And if you compare that with the previous results, this was not a positive proportion. It was p to some exponent less than 1. So that's why we get actually a good improvement. This was the case of an odd number k, progression length 5 or 7. And so in the case of k is even, actually, it looks much more complicated. So what we got, more or less, we wanted to have a general result. And what we got is of the following type. We have such an interval as before, and we have one extra element. Yeah, so lifting from, say, going from k equals 5 to k equals 6 is a bit disappointing. We get one extra element in the base. And moreover, we have a restriction, namely m must be in a certain residue class modulo k. So that such an expression actually can be built. Also, well, what I said works particularly nice if m is a prime, and if m is a composite number, you could actually do something similar with if the smallest prime factor is larger than k. So this is to avoid certain cyclic substructures. Right, with Peter Palpach, I also studied some cases if the base is a prime power. And with Peter Palpach, we also studied, say, cases, say, instead of avoiding, say, 3 progressions, modulo 4, avoiding 4 progressions. So in small dimensions, we worked out explicit examples. And if you work modulo 4 and avoid 4 progressions, now lifting up in this situation is the best we can do. But avoiding 3 progressions, so k is 3 and mod 4, lifting up is much weaker, because I told you earlier it should be of size 3 to the lower bound is of size 3 to the n over square root of n. Right. Okay. I think I'm skipping. So that was a slide on motivation or connection to the integer case, and here I want to give you a heuristic reason why you should expect that in this case modulo 4, the number of points in this cube cannot be too large. So you take a subcube, so to say. Yeah, if you're in the cube of dimension here 3, you have a 4 to the n cube, and then you take a 2 to the n subcube here of 8 elements of the 64, and yeah. So the whole cube consists of this substructure, also in many shifted copies, of course. And now, if you add one extra point, or say you have, if you have any, take the two crosses here. You have 2 points, and then you want to avoid a 3 progression, and you realize you must avoid this point and all the other points. So just 2 points tells you have to avoid such a subset of 8 points. And then you go on. If you have 3 points which are not on a line, you will avoid lots of substructures. You will avoid all of these. And then you go on again. You take a 4th point, which is not on the same plane. And then you see, even just with 4 points, these are the red points here, 3 and another one, 4. And then you see almost everything is forbidden. So you have the substructure, the cube of size 4 to the n is substructured into lots of cubes of 2 to the n cubes of 2 to the size 2 to the n, and if one of these subcubes of size 2 to the n, there are, say, 4 or more points, then more or less everything else is forbidden. So this gives you a good heuristic why such sets shouldn't be too large. Right, and I think I can skip this because it's similar. Yeah, let me say the final message more or less. So the previous people studied often local constructions. We call this local if you have a finite dimensional example lifting. What we have, we call it a global construction, because you really go directly to dimension n and you just restrict the digits in a relatively weak way. And so these explicit constructions look quite strong. And certainly stronger than what the probabilistic method would give. Okay, thank you very much.
Okay, you can read the question.
I can read the question. The question is, I said I have an improvement for caps if the prime is 5 modulo 6. Actually, we do not really have a good answer for this. I believe it has to do with, when I said lots of linear equations are equivalent, we just believe that reducing the number of equivalent equations works in a slightly better way. And it could have to do with, yeah, so modulo 5, or say 1 mod 5 or 5 mod, 1 mod 6 or 5 mod 6 have a different structure, of course, with quadratic residues or non-residues. It could have to do with this. The reason why we did not really investigate this, because we have just finitely many primes only, and we have no hope that our method without further ideas can be improved. The reason is, for larger primes you have more linear equations to consider, and this reducing the number of equations might save you a factor of something like 4 or 6. And if p is large and you have to care for p over 6 linear equations, this seems to be too restrictive, so that the sets, digit sets, can be too small. That's why we thought also, okay, we have this observation with 5 mod 6, but it's not so central.